Pleasant day everyone, we are Group TTNT. With the government push on EV and renewable energy by introducing green technology tax incentive in budget 2024, there will be a need to have a study on Malaysian distribution network to ensure the stability of our local grid. There are multifaceted challenges that need to be solved and prepared to ensure both stability and good profit margin for parties that are interested to pursue into this industry. To ensure the validity of our work, there are a few norms and standards that need to be followed. For instance, like EVR, ISO 15118 and IEC 61851, and many more are stated in our report. Transformer data are taken from Tesla company and cables are from Southern Cables. PV model data are taken from AE Solar, and lastly, EV, we will have 4 different models for this simulation. Simulation is done by using dead silence software with most of the parameters given, but some are calculated or found from company data. For example, like ampacity and distance between nodes, that is set to be around 10 meters. All of the PV and load are set with its time characteristic. The impact study are from a few simulations. This includes power flow analysis, short circuit analysis, and quasi-dynamic simulation.
Next, we modify the houses into prosumer by integrating PV panels into the basic LV distribution network. This means the houses not only consume power but also generate energy through solar irradiation. To assess the impact of PV-DG on the distribution network, we perform power flow analysis for 0 to 200% penetration level at 1 pm when the PV-DG generation is highest. This simulation aims to study the PV-DG integration in a worst-case scenario characterized by high PV-DG generation and low load consumption in the distribution network. The network voltage remains within the acceptable range of -6% and +10% for all penetration levels. The power drawn from the grid decreases with increasing PV-DG penetration because active loads are supplied by PV-DG generation. When the PV-DG generation exceeds network loads, reverse power flow begins at 50% penetration. This surplus generation flows back into the grid, peaking at 126 kilowatts at 200% penetration. A similar trend can be observed in average line thermal loading, transformer thermal loading, and distribution network losses. These network parameters follow a decreasing pattern as the penetration level of PV-DG increases up to a certain threshold. However, beyond this threshold, the pattern transitions into an increasing trend with further increases in PV-DG penetration level. For example, average line thermal loading decreased when the PV-DG penetration level was increased to 25%. After that, it turned into an increasing pattern when the PV-DG penetration level increased further to 200%. The fault level at each feeder was observed to have a linear increasing trend as the PV-DG penetration level increased from 0 to 200%. The rise in fault level is caused by short circuit current from the higher number of PV-DG equipment in the network. Feeder C has the highest fault level compared to other feeders due to its shorter cable length and lower line impedance.
Now, let's look in a modeling of EV profile. We have identified 4 different types of EVs, each having a different profile, especially target on different AC charging power, 3.7, 7.4, 11 and 22 kilowatt. Our simulation have different start charging time ranging from 6 to 8 pm with all EVs maintaining a maximum discharging which is SOC for between 20 to 80%. First on our list is the BMW X3 PHEV model which has 3.7 kilowatt charging power and 12 kilowatt hours battery capacity, allowing for up to 41 kilometers of emission-free driving. To analyze different scenarios, we have simulated 2 start charging times 6 and 7 pm. Next up is the BYD Atto 3, a BEV with a 7.4 kilowatt charging power and a 60.5 kilowatt hour battery capacity, providing a range of up to 480 kilometers. So our simulations focus on charging time of 6 pm. The third EV in our lineup is the Tesla Model Y, a BEV with an 11 kilowatt charging power and 75 kilowatt hour battery capacity, allowing for up to 533 kilometers driving. For simulation purpose, we have chosen a start charging time of 7 pm. Lastly, we have selected the Porsche Taycan 4S model for the fourth profile, known for its remarkable 22 kilowatt charging power, the highest in the market. The Taycan has a 79.2 kWh battery capacity and a range of 408 km driving range. The simulation involved a start charging time of 7 pm.
Let's talk about the simulations. The EV load is added to each house
and the characteristic of EV chargings can be modified based on what we have discussed before. There is total 4 profiles that will be discussed in this video. For the first profile modeling, which is BMW X3, the time is starting from 7 PM to 9 PM. Based on the simulations, we can see that the thermal loading and voltage is not always violated. But we also proved that the network indicates the thermal loading violations on transformer, which is 82.9%, when EV penetration is equal to 100%. Hence, the recommended safe EV penetration level for this profile is 80%. Let's move on to the second profile, which is BYD Auto 3. The charging time is from 6 PM to 11 PM. From 0 to 100 EV penetrations, the voltage violation level is still acceptable, but it is approaching to the limit as the EV penetration increase. Same goes for thermal loadings of feeder. However, the transformer indicates 89.12% thermal loading violations starting from 60% of EV penetrations. In conclusion, the safe level of EV penetration should be maintained at around 40% maximum. Next will be Tesla Model Y. The charging time is from 7 PM to 11 PM. From the result, starting from 40% of EV penetrations, the network indicates thermal loading violations on transformer, which is 89.5%. Based on the graph, we can see that there's also voltage and thermal loading violations occur at feeder E, when EV penetration is 100%. To make sure a healthy network, only 20% of EV penetration is accepted for this profile. Lastly will be Porsche Taycan. The charging time is from 7 PM to 9 PM. The network indicates 89.5% of thermal loading violations on transformer, even only 20% of EV penetration level. Moreover, there's also voltage and thermal loading violations occur at feeder E when EV penetration is equal to 60% based on the graph. Hence, we can conclude that the network is not suitable for adapting the Porsche Taycan charging without any mitigation measure. In conclusions, the safe level of EV penetrations for each profile are shown. When the EV penetration increases, the network losses is also increases. Besides, feeder E shows the maximum thermal loading and the lowest voltage per unit during the simulations. Therefore, feeder E has the potential to be recognized as a critical feeder.
Now, let's discuss the impact of ESS intervention in the LV network. We are looking at 2 types of ESS for this study, feeder type ESS and grid integrated ESS. There are 3 scenarios in total, with the first scenario involve feeder type ESS discharging power based on the presence of EV load, the second using grid integrated ESS, and the third being a special scenario with feeder type ESS discharging based on the reverse power flow strategy. Starting with feeder type ESS, the system is specially designed for a critical feeder, which in our case is feeder E. The ESS sizing is 500 kW, which is determined by the surplus power generation of feeder E, which is approximately of 480 kW. In the first scenario, after the interventions of ESS, the result show a slight improvement in the safe EV penetration level across 4 different EV profiles. Refer to the table below for comparisons of the safe level before and after ESS intervention. In this scenario, the ESS will discharge energy only when EV charging load is present in the grid. While this ensures effective peak shaving for the critical feeders, a downside is that most of the energy will go unused even if the consumer load exists. Now, let's turn our attention to scenario 3 before discussing grid integrated ESS. In this scenario, we randomly selected an EV profile to simulate, as the behavior of all simulations will be similar. Hence, the ESS discharge when reverse power flow ends at around 6 PM, fully supporting the grid load, including consumer and EV charging load. The advantage is a reduction in grid load and a slightly higher increase in the safe level of EV penetration as compared to scenario 1. However, the downside is that the energy capacity might be insufficient to fully support the grid during the peak hour as seen in the BYD graph. Around 10 PM, the ESS energy dropped to 20% of its SOC and stops discharging, resulting in the loss of the peak shaving objective. Now, let's explore scenario 2, which simulates the use of grid integrated ESS discharging only when EV load exists in the grid. For this case, the grid integrated ESS sizing is 2 MW energy capacity based on the surplus PV generations from the LV network, around 1.8 MW installed at the substation level. In this scenario, the ESS successfully reduced voltage drop among the feeders, lower thermal loading for DN components, and decreased energy losses. The results are evident in the new safe EV penetration level, which shows almost 3 times greater compared to LV network without ESS intervention and almost 2 times greater compared to scenario 2 as shown in the table. This is because ESS can supply a sufficient amount of energy to the grid to cover the EV load demand. In summary, feeder-type ESS act as a viable option, effectively addressing issues with the critical feeder. When compared to a huge investment in grid-integrated ESS, which involves spending more on building larger ESS at substation levels, the feeder-type ESS solution is more affordable and allows for a minor improvement in the safe EV penetration levels. For grid-integrated ESS, where cost is not a limiting factor, it proved to be a superior alternative for LV network optimizations. Unlike feeder-type ESS, which target critical feeders, grid-integrated ESS offers a scalable approach by efficiently increasing the safe EV penetration level.
One of the mitigation measures that we propose is the time of use tariff, also known as TOU tariff. It is the time differentiated electricity prices offered to the customers so that the controllable loads can be shifted away from the peak periods. By incentivizing consumers through electricity tariffs, they will avoid using large energy-consuming devices such as EV chargers during peak hours. Power flow analysis shows that the feeder loading drops around 5% during the flat period when the initial charging time is shifted away from 6 p.m. to 2 a.m. This is because the sum of residential and EV loads becomes lower during a flat period. Besides lowering the feeder loading, charging EV during a flat period saves 18.2 cents per kilowatt hour compared to the peak period, which converts to 5 ringgit and 40 cents for a 4-hour charge. Therefore, the TOU tariff mitigates the strain on the feeder while also providing cost-saving benefits.
In normal cases, solar inverters only inject active power into the bus. Therefore, during broad daylight, the active power of PV will increase and from the grid will decrease, causing a decrease in power factor. To overcome this problem, reactive power can be injected through the inverters like what TNB initiative on smart grid to have, while optimization. Reactive power regulation has shown significant result by around 10% in majority of allocational case. Using reactive power regulation have gone near to the limit with 100% PV penetration. As an additional mitigation, Malaysia can adopt the practice of localized demand control. As many smart grids are in the process of building, our suggestions are to combine direct load control and indirect load control that can ensure the speed and dependability with data privacy. According to the result done by Tublin in New Zealand, LDC approach successfully reduced grid congestion. At a minimum LDC participation rate of 40%, the local grid network can achieve complete resilience against overloading and congestion. In short, our group managed to study the impact on PV-EV integrated to grid through power flow analysis, short circuit analysis, and quasi-dynamic. A few mitigation solutions including the usage of ESS and time of use tariff also have shown the best success toward mitigating the voltage violation and thermal loading of distribution network.
That is all from our team. Thank you.